No, that is the wrong link. So if you ended up here, which I don't think any of you, if you use the QR code, you shouldn't have ended up there, right? You ended up at the other one that looks like, yeah, cool. So let's go fix that real quick. So let's go to Canvas. For a second. Log in. And the link to the attendance form is in like 1,000 different places. So you should be able to find it. I would go here, because I know where it is over here. There we go. The link to the attendance form. It's the right link. Be really dumb. Oh, cool. Yes, that is what it should look like. So when you fill out the attendance form, that is what the link should look like. Let me grab it for you, Caleb, so you can have easy access to it. It's kind of lengthy. I can shorten it later, but for now, this will do. So please fill out that form when you have a chance. Everybody else as well, please fill that out when you have a second. I noticed, so let's see, I know most of you said on Monday that we're here that most of you were in Casal's class, is that right? Except for Caitlin, who's in Alameda's class. What about the Patrick? Whose class are you in? Okay, and Dylan? And Ellie? Okay, so mostly Casal still. So Alameda hasn't responded to my email yet, but it's fine. It's early in the quarter. Professor get a lot of emails. And I see that Casal still hasn't yet posted a homework assignment. That's right. Yeah, I just looked this morning and it still says coming soon. Like, okay, so we will continue on in the direction that makes sense, which is talking about sequences and series. And if there are things you want to see or talk about, you're welcome to let me know. What time? Oh yeah, it sounds like we should get started. Okay, so let's see. Make sure we don't do this anymore. Just as a quick, for those of you that weren't here on Monday, just a quick. Here's Canvas. I would say the modules are where you're going to find anything useful. The link to the attendance form, the link to the Zoom if you don't want to come in person. I definitely recommend coming in person, but totally fine to come on Zoom. My office hours, the YouTube playlist if you want to watch the video later and then fill out the attendance form. Please do fill out the attendance form whenever, however you attend. That's how we keep track of things. Links to the class notes, which I will post, some useful resources. And then also I will post the class videos and the notes here as well. You can find, there's like 3 different places to find everything because it's trying to make it relatively easy. And then some maybe useful stuff from 21B and some series handouts already from 21C. So once we start talking about like the tests for convergence and divergence, these handouts I think are fairly useful, a good source of reference. And then some exam prep material, which yeah, we'll get to that later. And then lots of old recordings. If you really want to go watch me say the same stuff again, you certainly can. Yeah, I think that's the quick and dirty. Let's do this. That could be a little brighter, I think. Yeah, I feel like there was something else I was really wanting to say, but I have to remember it. Let's see. So Co-21C. Today is April 5th, 2023. Last time I had mentioned that we were going to talk about this sequence, the sequence AN equal to, I really want to do it the other way, but fine, we'll do it this way. N factorial over 4 to the N. And I mentioned that this one definitely does diverge because a factorial is always going to outpace an exponential thing or grow faster. I usually like to, the phrase I most commonly use is outpace. If one thing grows faster than another one, eventually it will outpace it and go to infinity faster than the other thing goes to infinity. The issue with this type of infinity over infinity type of sequence or limit is if you try to take the limit as n goes to infinity of n factorial over 4 to the n, it certainly is an infinity over infinity type, but unfortunately, when you have a factorial, we cannot use L'Hopital's rule because we can't take the derivative of n factorial or x factorial, whatever. It's not a nice continuous function. It doesn't differentiate well. There are ways in more advanced math classes where you actually can talk about taking the derivative, but it's weird and not what we're here for. So instead, the way we're going to see that this thing actually grows, this limit is divergent, the sequence diverges, the limit's infinity, is by writing out some terms. And your teacher may or may not go over this, I don't know, but I think it's worth seeing at least once just to really kind of believe that this limit actually goes to infinity. Some people might write this as infinity over infinity to emphasize the larger nature of the factorial and the smaller infinite nature of the ordinate. So if we start writing out terms, it's going to be in our interest to kind of not write things out simplified. So instead of writing like, 4 factorial is 24, I'm just going to write 1 times 2 times 3 times 4, which is going to be a little bit of pain, but let's see here. So we've got a sub 1, that's just going to be 1 over 4 to the 1. A sub 2 is going to be 1 times 2 over 4 times 4. A sub 3 is going to be 1 times 2 times 3 over 4 times 4 times 4. So you'll notice so far that my terms are actually getting smaller, right? In this one here, I multiplied 1/4 by, oh, that's not my pen. I want that pen. I multiplied 1/4 by 2/4. So this is actually equal to 2/4 times the first term. Smaller than the first term, right? I multiplied by a number less than 1. And this number here, if I think about this 1/4 times, this 1/4 times 2/4 being my second term, this is really 3/4 times my second term. So things are getting smaller in the beginning, but then they stop getting small. Because when I look at A4, that's going to be 1 times 2 times 3 times 4 over 4 times 4 times 4 times 4. And now from the previous term, I multiplied by 1, right? This is 1, and 1 times 2 times 3 over 4 times 4 times 4 is my previous term. So it stayed the same. And now we're going to start multiplying by things that are going to make it bigger. Because on the top, I'm going to multiply by numbers that are larger than 4. On the bottom, I'm going to keep multiplying by another iteration of 4. So my a sub 5 is going to be essentially 1 times 2 times 3 times 4 times 5 over 4 times 4 times 4 times 4 times 4. My previous term times 5/4. So things are getting bigger. And that might be enough to kind of justify to ourselves, yeah, this thing's going to get infinitely large because we're just going to keep multiplying by numbers that are going to get larger and larger and larger and larger. If you wanted a more rigorous proof of how this limit is infinitely large or diverges to infinity, you would have to do something like this. Yeah, it's kind of a pain, but we can do it. It doesn't take too long. So the way you would do this is you would kind of say, like, I want to look at a sub n. It's going to look like, I'm gonna break this up in a very specific way. So it's going to be n factorial on top and 4 to the n on the bottom, which I'm going to write out as n over 4 times a bunch of other terms, n minus 1, n minus 2, all the way down to 6 times 5 over 4 times a bunch of 4s. Same number of terms on top and bottom, right? Because 4 to the n and n factorial have the same number of terms. They both have n terms. And then finally, the last 4 terms here, 4 times 3 times 2 times 1 over 4 times 4 times 4 times 4. So I've written out this in kind of a silly way, but there's a point or a method to this madness. This 4 times 3 times 2 times 1 over 4 times 4 times 4 times 4, we know what that's equal to. That's equal to, I don't know, 6 over 64. I don't really care what it's equal to. I just care that it's a constant. And then importantly, here's the important part here. This section here, if you look at each of those if you look at each set of terms as individual fractions, each of those fractions is bigger than what? Yeah, each of those is bigger than 1. 5/4, 6/4, all the way to whatever this is, whatever this is. So this entire fraction has to be bigger than 1 because it's a bunch of stuff multiplied together that's all bigger than 1. So here's what I can say about this sequence. This sequence, n factorial over 4 to the n, it is definitely bigger than n over 4 times 1 times 6 over 64, which I know feels kind of silly, whatever. So then what I can say is, great, if a sub n is bigger than n over 4 times 1 times 6 over 64, then the limit as n goes to infinity of a sub n is definitely bigger than the limit as n goes to infinity of n over 4 times 6 over 64. But 6 over 4 times 64 is just a constant, and n is going to go to infinity. So this limit is for sure infinity. It's kind of a weird thing you have to do when you do this kind of limit with a factorial, but it totally works. So we break up this piece and say it's bigger than 1. This piece is just a constant that's not 0. And then our terms are bigger than this, and this thing is getting infinitely large. So our thing is getting infinitely large as well. It's kind of neat. It's kind of not super necessary. The takeaway here is that n factorial outpaces any exponential b to the n. That's what I would take away from this. Questions about any of that? Couple other sequences we'll talk about. There are some interesting things that are definitely going to come up a lot in this first half of 21C when we talk about sequences and series. And then we'll talk about vectors and other stuff. I kind of forgot, there was one other thing I forgot to mention, not that we need to know the big picture, but we also do talk about functions of 2 variables and maximizing, minimizing, things like that. That was something I kind of forgot that we do at the end of 21C. So we will do that as well. Let's look at a couple other examples. Ooh, this is one of my favorite examples. A sub n equal to, oh, by the way, Caleb, also, you're certainly welcome to unmute yourself and ask questions if you want to, or write something in the chat. If you write something in the chat and I don't see it right away, just say something or let me know, but I'll definitely see it eventually. And let's look at this very well-known sequence. A sub n equal to 1 plus 1 over n to the nth power. May not be well known to you yet, but it will be. So if we start writing out terms, let's see. So if n equals 1, I get 1 plus 1 to the 1, which is 2. If n equals 2, I get 1 plus 1/2 squared, which happens to be 9/4. If n equals 3, I get 1 plus 1/3, which is 4/3 cubed, and so on. If n equals 4, I get 1 plus 1, so 5/4 to the 4th, 6/5 to the 5th, and it just goes on and on and on and on. You plug in n equal to 100, and you get 1 plus 1 over 100, which is going to be 101 over 100 to the 100th power. You might wonder, you might think, this looks like this might be getting close to 1, because the inside of the parentheses is pretty close to 1, right? That's 1.01 to the 100th power. But if you actually plug that into a calculator, it's not going to be anywhere close to 1. I didn't bring my calculator, and I really hate using my stupid phone calculator because it just never feels particularly convenient, but I will anyway, just to show you all. If you do 1.01 raised to the 1.01 to the, where are we at here? To the 100th power, you get 2.7. You might remember there's a number that's really special that's close to 2.7. It's E. So what's happening with this sequence is the limit of the sequence is actually E. Now, this is what's called an indeterminate form. It's a 1 to the infinity indeterminate form. And it is true that the limit as n goes to infinity of 1 plus 1 over n to the n is equal to E. Now, should we prove it? I think we should. I think it's worth seeing it at least once to really. So here's what I'll say. People are going to throw this limit at you fairly often and expect you to just kind of do it or to manipulate it easily. But it's good to see it at least once so we can kind of believe it for real. There's a couple different ways to attack this. I personally like to rewrite it as the limit n goes to infinity of e to the natural log of 1 plus 1 over n to the n. And I guess a little backstory here, I should really say, whenever you have an indeterminate form like 1 to the infinity or 0 to the 0, or more generally an exponential indeterminate form, we're probably going to end up using L'Hopital's rule. But you can only use L'Hopital's rule for specifically the indeterminate forms infinity over infinity or 0 over 0. I really should say plus or minus infinity over plus or minus infinity. It doesn't matter what the sign is. But those are the only times you're actually able to apply L'Hopital's rule to a limit. So if you have some other indeterminate form, like 1 to the infinity, that's not a fraction. I can't use L'Hopital's rule yet. So I have to manipulate it. And the only manipulation that really works is by taking the natural log and getting that n out of the exponent. So the whole reason we did the e to the natural log was so that this n here can come down in front. So we're going to rewrite this as the limit as n goes to infinity of e to the n times natural log of 1 plus 1 over n. Still not a fraction. So I'm going to do one more thing. So I will point out at this point, you have something that is n's going to infinity, and natural log of 1 plus 1 over n is going to natural log of 1, which is 0. So you have an infinity times 0 indeterminate form, which you still have to manipulate. And finally, we're going to rewrite this as the limit as n goes to infinity of e to the natural log of 1 plus 1 over n. Instead of multiplying by n, we're going to divide by its reciprocal. Divided by 1 over n. And now we have a 0 over 0 type of indeterminate form. And we can finally actually apply L'Hopital's rule. You could, and I guess I will. Some people like to rewrite this where the limit passes through the e to the whatever, and write this as e to the limit as n goes to infinity of your stuff, natural log of 1 plus 1 over n, over 1 over n. That step isn't particularly necessary, but it makes it look a little bit nicer. So now, finally, the L'Hopital's rule. I get e to the limit as n goes to infinity. I do the derivative of the top. Okay, the derivative of the natural log of some stuff is 1 over the stuff times the derivative of the stuff. And the derivative of 1 plus 1 over n is 0 plus n. The derivative end of the negative 1 is negative n to the negative 2, or negative 1 over n squared. And conveniently on the bottom, the derivative of 1 over n is the same. It is again negative 1 over n squared. And those cancel out, which is great. They're perfect matches. And so then we can actually take the limit now. The rest of this here, well, 1 over n goes to 0 as n goes to infinity. So we end up getting e to the 1 over 1 plus 0, which is just e to the 1. Which is e. A couple notes on this. Some people do this slightly differently, and they just say, let's take the natural log of the whole thing and then do the limit of that. And then at the end, they get an answer that's 1. And they're like, oh, but really we have to do e to our answer because we started off with, we have to undo the natural log that we did. Pocket. My clock looks, I guess that's right. I just looked off. Okay. Anyway, sorry. Questions about this? Yeah.
Like when to apply them.
Right. So the only time we can apply L'Hopital's rule is when we have either a 0 over 0 type of thing or an infinity over infinity type of thing. And also, unlike in our previous example, be able to take the derivatives of both functions. Because if you can't take the derivative thing, you can't use L'Hopital's rule. Right. So here's what I would say. And again, this will come up sometimes in this class, but not a whole lot. There are 3 types of indeterminate forms where eventually you will probably have to use L'Hopital's rule if you want to take the limit. So for example, that's not a great example then. So I'll point them out, but they don't always come up. So when we talk about sequences, we're usually talking about n getting large, right? But there are some other things. So 0 to the 0 is what's called an indeterminate form. So for example, I would just point out, if someone said, if we wanted to find the limit as x goes to 0 from the right of x to the x, this is another example where you'd have to use L'Hopital's rule eventually by first doing this whole e to the natural log thing. We're not going to do it because it's not really what's going to come up in this class, but it is an example of how you might need to use L'Hopital's rule. We would write this as the limit as x goes to 0 from the right of e to the natural log of x to the x, and then the limit as x goes to 0 from the right of e to the x times natural log of x. And then finally, before using L'Hopital's rule, the limit as x goes to 0 from the right of the natural log of x over 1 over x. Because writing it like this, oh, I forgot the e. Good job. As x goes to 0 from the right, 1 over x goes to infinity, and the natural log of x goes to negative infinity. It's good to think about the graph of the natural log of x, be like, oh yeah, as x goes to 0, the natural log of x goes down to negative infinity. So at this point here, you have a negative infinity over infinity And then you can apply L'Hopital's rule. The other type of exponential indeterminate form is, oh, what is it, James? It's an infinity to the zero. And we probably could make up one like this that would make sense. Let me think for a second here. Let's actually, and then of course, 1 to the infinity. So the example for 1 to the infinity, we already did one. It was, like the limit as n goes to infinity of 1 plus 1 over n to the n, and it was e. For an infinity to the zero, let's go to the next page and not try to just cram it in here. So is there one on here? Yeah, no, not really, but fine, we can make it up. So let's say we had a sequence that was, oh yeah, of course. I'm sorry, I'm being silly. I don't know. We'll work something out. Let's say we had a sequence that was, I don't want to make this really dumb though. Oh, fine, we'll try that. So it's always worrisome when I just make something up because I'm like, oh, we'll see. Let's see if we had n to the 1 over n power. There's a sequence. Let's write out some terms. So if n equals 1, I get 1 to the 1. If n equals 2, I get 2 to the 1/2, or the square root of 2. If n equals 3, I get the cube root of 3, the 4th root of 4, and so on and so on and so on. The 100th root of 100. My guess is this limit's going to be 1, but I don't know. So I really should say this as, does this sequence a sub n equal n to the 1 over n converge or diverge? That's usually the question at play. And so to answer it, we're going to take the limit as it goes to infinity. Okay. I'm going to do this one the other way, meaning instead of doing e to the natural log, I'm just going to take just to show it both ways. I'm going to take the natural log, and then at the end, we will undo that natural log with an e to the whatever answer is. So let's examine, or I like to say, let's look at instead the limit as n goes to infinity of the natural log of n to the 1 over n. And again, why are we using a natural log even? We have a problematic exponent, right? We don't really know how to deal with what this is doing. So what we're going to do is we're going to take the natural log, which allows us to bring down the exponent and eventually get something that looks fractional. This one actually works out very quickly. I'm going to rewrite this as the limit as n goes to infinity of 1 over n times the natural log of n. And then it's already actually written as a fraction. I just didn't write it that way. I should have written it as the limit as n goes to infinity of the natural log of n over n, which we can see is an infinity over infinity type. Natural log of n, although slowly, does go to infinity as you go further and further and further out, and n certainly goes to infinity. If you had to guess, based on knowing that the natural log of n grows much, much slower than n does, if you had to guess what this limit was going to be, what might be a good guess? Yeah, 0 is a really good guess because the natural log is just so much smaller than n. N is going to outpace natural log of n for sure. So using L'Hopital's rule, though, just to be rigorous, we take the derivative of natural log of n, we get 1 over n. We take the derivative of n, we get 1. And oh yeah, of course that limit is 0. That's not our answer though, right? We took the natural log, we have to undo that and say, okay, our actual answer is going to be e to the 0 that we just got. Which is 1. So if you do it this way, you have to remember at the end to go back and say, oh, my real answer is e to the whatever number I got. Yeah. So general statement. So in general, because the one that comes up the most often is the previous one we kind of did. In general, the limit as n goes to infinity of 1 plus any number over n you want, I'm going to call it x over n to the nth power, is going to end up being e to the x instead of e to the 1. So in our previous example, right, we totally had the same thing. I'm just to cover that for a minute. We had, right, the limit of 1 plus 1 over n to the n ended up being e to the 1. Well, if you change that 1 to any number you like 2 or 5 or pi, the answer ends up being e to that number. So just to kind of give an example, the limit as n goes to infinity of 1 minus 2 over n to the n, well, really that's the limit as n goes to infinity. I would write it as 1 plus negative 2 over n to the n and be like, oh, that's just going to be e to the negative 2. And I think probably at some point, the expectation of your teacher is that just people do this instead of doing the whole process where you take the natural log and step down and all that kind of jazz. So usually as we move forward, there's kind of just oh yeah, students know how to do this. I'm going to let them do it this way and expect that they do it this way and not do all of that process. Yeah, L'Hopital's rule is definitely in play. Cool. The other thing we sometimes talk about with sequences, which is, yeah, sometimes is not right. We do talk about sequences. It's kind of working backwards. And instead of being given the formula for the sequence and kind of figuring out if it converges or diverges, sometimes we're just given the terms of a sequence and asked what the formula is. So for example, we want to find formula for a sub n. I always lose track of the number. That's fine. We're in a new section. I'm going to start with number 1. So let's start with something relatively straightforward. 6, 10, 14, 18, 22, etc. I think we can see here that the difference in each term is 4. So typically when I'm looking at a sequence, I usually start by looking at differences in terms. So that's a 4, that's a 4, that's a 4, that's a 4. This is what's known as an arithmetic sequence when you keep adding the same number every time. This is a medic. And here's what I always think about when I'm trying to find the formula. When you are writing your terms, so this is, this is a sub 1, a sub 2, a sub 3, a sub 4, a sub 5. The subscript or the index, a sub whatever, is always increasing by 1 every time. So if you're trying to increase by 4 every time, you just want to take the thing that's increasing by 1 every time and multiply it by 4. So we know that our sequence is going to look something like a 4 times n plus something, or maybe minus something. Since I want to start at 6 and n is starting at 1, well, if I plug in 1, I'm going to 4 times 1, I need to add on a 2. Now, the way we've written this does make the implicit assumption that n is starting at 1. There are literally an infinite number of other ways you could write the sequence if you wanted to. You could totally write it as an equal to 4n plus 6, where n is starting at 0. That would also be totally legit and fairly normal. On the other hand, you could write some other really less normal things that would still be correct, but just kind of strange to do, right? If you really wanted to, you could write this as, let's say we're going to start at n equal to 100. You could write this as an equal to 4n. I want to end up with 6, so minus 94, where n was greater than or equal to 100. That would also technically be a correct way of writing the sequence. It's just not typical. So usually, if you have the choice, you want to start your sequence at n equals 0 or n equals 1. Usually 1 is my probably default setting, but 0 also has uses often. Let's look at some more interesting examples. Let's say we had something like the sequence 5/8, comma 7/11, comma 9/14, comma 11/17, etc., etc., etc. Typically, when I see things written as fractions, I treat the numerator and the denominator totally separately. There might not be always the right thing to do, but I think it's always the right thing to do when you start. So looking at the numerator, I see a difference of 2 every time. Great. And looking at the denominator, I see a difference of 3 every time. Also great. That's easy. So then I'm pretty sure my sequence is going to look something like 2n plus something over 3n plus something. And then the way I figure out the something is just by plugging in n equal to my starting value, which could be 1, could be 0. So if I say, okay, great, a sub 1 is going to be 2 plus whatever over 3 plus whatever, and I need it to equal 5/8, well, that means that needs to be a 3 right there, and that needs to be a 5 right there. So my sequence really is a sub n equal to 2n plus 3 over 3n plus 5. That gets me the right thing being added in both the numerator and the denominator every time, and also the right starting place. I don't think you need to specify that you're starting at 1, but I like to, just to be safe. This is not an arithmetic sequence because we're not adding the same thing every time, writing the same thing to the numerator and the same thing to the denominator every time. That's not, we're not adding 2/3 every time. It's just not. Yeah, what time is it? Okay. Questions so far? I mean, you're always welcome to ask questions. There's a lot of things to say in the beginning, so I feel like I'm just kind of going and going and going. But if you want me to stop and clarify something, yeah. Doesn't have a name. Really, and I would say usually we don't really care about the names with a couple, well, maybe with a few kind of exceptions. I don't really like arithmetic sequence, big deal. No one cares. It's called that. It is, but it does have that name. The next one we're going to look at has a name as well. And it actually is an important name that you will see for a while throughout the quarter. So let's say we have the sequence. Sure, let's go 5, 10, 20, 40, 80, et cetera, et cetera, et cetera. So here, if you started off the same way we started off before, it's not going to get you anywhere really. If you start thinking about differences, okay, the difference here is 5, difference here is 10, 20, 40, 80. And if you kept, 80, not 88. If you kept doing, oops, I said 20, I wrote 10. If you kept doing that, you just get the same pattern over and over again, right? The difference between these things are 5, 10, 20, 40, 80, etc. So when you see this repeating kind of, the differences are the same no matter how far down you go, it's kind of like, when I talk about the difference between terms, it's kind of like the derivative, because the derivative is kind of like the difference. In fact, if you look back at this first example we did, the difference between all these terms is 4. And what's the derivative of 4n plus 2? 4. Not a coincidence. It's very much happens that way because of the nature of how things are working here. So when the differences are always the same, no matter how many times you take them, what's an example of a function that essentially stays the same no matter how many times you take the derivative? You know one. There's definitely a function that when you take its derivative, it doesn't change. E to the x. More generally, exponential functions don't really change. Like for example, the derivative of 2 to the x is almost the same. It's 2 to the x times natural log of 2. Or 3 to the x would be 3 to the x times natural log of 3. So any kind of exponential function, the difference doesn't really change. And this is exactly kind of that. This is an example of an exponential function. And what's really happening here is every time, instead of having the differences be the same, we are actually multiplying by the same number. 5 times 2 is 10. 10 times 2 is 20. 20 times 2 is 40, et cetera, et cetera, et cetera. So what we have here is essentially a sub 1 is 5. A sub 2 is 5 times 2. A sub 3 is 5 times 2 squared. Right? Every time I'm just multiplying by another 2. A sub 5 is 5 times 2 to the 4th. A sub 6 is 5 times 2 to the 5th. And so what I would notice here is that essentially the power I have on 2 is the thing that's increasing by 1 every time. And so I'm just going to relate that to my index. Notably, that power is always 1 less than my index. So I would write this as a sub n equal to 5 times 2 to the n minus 1, where n is starting at 1. But you could alternatively, if you feel like that looks just a little not as nice as it could be, you could prefer to write it as a sub n equal to 5 times 2 to the n, where n starts at 0. That would be literally the same sequence. This is an example of a geometric sequence. And the hallmark of a geometric sequence is that each next term is always going to be multiplied by the same ratio of the previous term to get to that value. So every time to get to the next number, we're just multiplying by the same ratio. In this case, it's 2. So we're always multiplying the previous term by some constant ratio r. To get to the next term. So the sequence does look like an exponential function because you have that 2 to the n, but I will tell you the name for it is a geometric sequence because that's just what we've all decided to call it. There's something else to say here. Oh, the other question is, does it converge? I guess well, I wasn't really, no, none of these converge to diverge yet. We forget convergence divergence. We don't want to do that. That's terrible. There's something else I wanted to say about this though. Yeah. How? Interesting. Sorry, I'm just looking at a few things here. Let's think about how much time we have. Let's look at one more example. Let's say we had something like terms being sure 8 and then negative 16 thirds and then positive 32 ninths and then negative 64 27ths, positive 128 81st, etc. Okay. Oh, always with the number. That's number 4. So this one I feel like looking at the differences seems kind of dumb. Maybe not. I maybe take it back a little bit. The first term feels not super useful, but if you look at all the other ones, I guess we have fractions where I should still look at the tops versus the bottoms. Here we can see that for the tops, or I guess I could write this as 8 over 1. That's helpful. The tops are always multiplying by what? 2. You could say 2 or negative 2. I was thinking 2, but then I was like, oh, but negative 2 would totally be possible. And then the bottoms, what are we always multiplying by? 3. And then there's also an alternating thing. So it looks like every time we're multiplying, I'm going to throw on the negative sign for the 2's because I want to put it somewhere. It looks like every time we're multiplying by negative 2/3. So here our ratio is negative 2/3. How do I want to say this? The way I would write the formula for the sequence, trying to do it as easily as possible. How would I do this? I would probably write this as 8 times negative 2/3 to the n, where n is starting at 0. Does that get me what I want? I think it does. So I plug in 0, I get negative 2/3 of 0 is 1, 8 times 1 is 8. If I plug in 1, yep, that totally works. Or if you like, you could write it as a sub n equal to 8 times negative 2/3 to the n minus 1, where n is starting at 1. There are lots and lots of ways to write the formula for a sequence. Yeah, I think we should skip that for now. Some people get really kind of into proving. So you should all, well, I will look for on your professor's website, but if he doesn't really say it, you should all let me know if he starts talking about the precise definition of a limit for sequences, kind of like back in 21A when we had to do delta epsilon stuff. Maybe had to do, maybe didn't have to do. That might come up proving some of these the limits of these sequences are what they are. But if some people don't cover that, so if it's not going to be covered, I don't feel like I need to burden you with seeing that. So definitely let me know if that comes up, but if it doesn't come up, we will not. You kind of did? Okay. All right. And that was in Casal's class? Okay. Let's go ahead and take a look at one example then. We got time, yeah. So let's say, let's do, yeah. This is where I'm gonna run out of room here. Yeah, let's use a whole new piece of paper. Always feels dumb, but fine. So let's use the precise definition of a limit. So when you see the words precise definition, there should be a space there. That is code for use a delta epsilon proof. To prove that the limit as n goes to infinity of 3n over n plus 2 equals 3. Alternatively, I could have said to prove that the sequence a sub n equal to 3n over n plus 2 converges to 3. Right? Those literally say the same thing, they're just written slightly differently. Okay. So I feel like we all know in our hearts that this limit is 3, right? We've done limits like this enough to be like, oh yeah, of course that should be 3. So how are we going to do this? Let's write out some terms. So writing out some terms, a sub n equals 3n over n plus 2. And my first few terms are going to be, let's see, 3 over 3, and then 6 over 4, and then 9 over 5, and then 12 over 6. And then, sure. One more, 15 over 7. They just go on and on and on. Okay. And if we take a look at this here, doing something graphical, we can see that 3 is where we're supposed to be getting closer and closer to. And our first value, so when we plug in 1, we got 1. We plugged in 2, it's a little bigger, it's like 1.5. And we plugged in 3, it was like 9/5, which is close to 2, but not quite 2. And then we plugged in 4, we did get 2. And then we're just, right, we're slowly getting closer and closer and closer to that value. So typically what we do here is we kind of just choose some arbitrary epsilon to kind of help us work things out. So let's pick, let's say epsilon equal to 1, which is essentially saying we want to be within one of our value that we think the limit is. So here's 1 below, here's 1 above. And we say that epsilon is 1. Then we can see that once we get to 4, we're good to go, right? If we're picking epsilon equal to 1, as long as n is bigger than 4, no problem. So if n is greater than, we usually say called capital N, the thing that we're setting to be kind of the place we're going to be bigger than, then we can see that our sequence a sub n, whatever it is, whatever value a sub n has, minus our limit, which we think is 3, is going to be less than epsilon. So the idea here is to find n in terms of just a general epsilon, so that for any, not just epsilon equal to 1, but for any positive epsilon, if little n is bigger than whatever that n is, then we get that r a sub n minus our limit, which we know is 3, is going to be less than epsilon. So that's the idea, right? We're just saying we need to go out far enough, right? If you want to prove the limit is equal to 3, you have to be able to go out far enough in the sequence so that you're as close to 3 as we say we need to be. Just like way back in 21, we're like, just prove the limit's the thing. You have to show that you can get close enough to whatever x is approaching. So the difference between your function and whatever you think the limit is as small as required. All right, so how do we do this? Well, usually we start with the thing we want to be true and kind of work backwards. So I'm going to start with, I want my a sub n, which is 3n over n plus 2, minus my limit, which is 3, to be less than epsilon. And then I'm going to work on this until I can get n to be bigger than something. Okay, I think we got enough time here. So let's see. So I'm going to do common denominator here. I want a common denominator? Yeah, I do. So simplifying this, I'm going to get 3n minus 3 times n plus 2, all over n plus 2. That simplifies to be 3n minus 3n cancels, and then minus 3 times 2 is minus 6. So minus 6 over n plus 2, less than epsilon. And then if we take the absolute values, we're just going to get essentially positive 6 over n plus 2, because n plus 2 is positive because n is going to infinity, less than epsilon. And solving for n, we can get, so I'm going to do some fast math here, right? So you can take as many steps as you want, but essentially what I'm going to do is I'm going to interchange the place of epsilon and n plus 2, right? I'm dividing both sides of epsilon and multiplying both sides of n plus 2. I'm going to get 6 over epsilon is less than n plus 2, or in other words, n has to be bigger than 6 over epsilon minus 2. And that is what we're going to choose our capital N to be. So that's the idea, is that we're going to say, great. So we can say that if n is bigger than capital N equal to 6 over epsilon minus 2, then it will be true that the difference between our sequence, 3n over n plus 2 minus our limit, will always be less than epsilon. So you can make epsilon super duper 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 small, and as long as n is far enough out, then you will be close enough to 3 that you can say, oh yeah, the limit has to be 3. You could actually pick a number if you wanted to, just to see, like, for example, let's say that epsilon was equal to 1 over 1,000. Well, great. Then 6 over 1 over 1,000 is 6,000 minus 2. That means our n is going to be 5,998. And as long as n is bigger than that, you go 5,998 places out. You plug that into this thing here, 3 times 5,998 over, let's just say 6,000, right? 3 times 6,000 over 6,000 plus 2. Worst calculator. I hate it. It's just not. I always mean to bring my calculator with me, and then I forget. I just need to keep it in my backpack. That's not even the right thing. I just want you all to believe me. I know you believe me, but I really want to just. I want to believe it. Yeah, sure. So 3 times. Oh, come on. Oh God, kill it. I should not need to do 3 times 6,000 on my calculator. I do know that that's 18,000, by the way. 18,000 divide. Oh, that's the problem with this one. 18,000 divided by 6,002. See, this thing is always, it's right. It's I know. I'm like, it's got like the thing in there. Yep, it's super duper close. It's definitely within 1/1000th of 3. Great. So that's kind of the idea of having to prove these limits of sequences if you have to. I guess it's 10:49. I probably shouldn't start a new example. So what I'm going to say is Friday, I'm going to probably try to look to wrap up talking about sequences, and well, kind of, and then start moving on towards series, which is really just, a series is a type of sequence. It's a sequence of what are called partial sums. So basically, just to kind of get you ready for what we're going to talk about next time, we're going to start talking about series. For like the sum from n equals 1 to infinity of 1/2 to the n. That just means add up all the things starting n equals 1. So this just means 1/2 plus 1/2 squared plus 1/2 cubed plus 1/2 to the 4th. And the reason I'm saying it's, so yes, it's a series or a sum, but it can also be looked at as a sequence of partial sums. The first partial sum is 1/2. The second partial sum is just the sum of the first 2 terms. The third partial sum is the sum of the first three terms. And the point I'm just trying to express here is that this thing here is called the sequence of partial sums. So although we should not call this a sequence, it is a sum or a series. Also technically is a sequence as well. So you might hear someone say, oh yeah, it's a sequence too. That's what they mean when they call it a sequence. That it's a sequence of partial sums. And then the idea is going to be, does this sequence of partial sums converge or diverge? That's kind of where we're going with this. All right, you've been great. It's been fun. I will get things posted in a minute. And yeah,